Welcome to the Solar Clips video series covering the basics of solar, photovoltaics, or solar PV. My name is Drew Chavone and I serve as an extension specialist with the University of Maryland. In our last video we considered some of the fundamental aspects and the rationale for grounding a photovoltaic system, and you can review that video for more information, but in today's video we're going to consider some additional aspects and some of the essential requirements for photovoltaic grounding, including code compliance with the National Electrical Code, or the NEC as it's commonly called. Of course, we can't address every aspect of grounding in this video, but a general understanding of electrical grounding, as we'll cover in this video, will help you to begin to design a safe and effective photovoltaic system. While electrical grounding is a complicated and often misunderstood concept, it does serve as a critical safety measure within all electrical systems and installations, protecting against electrical shock and ensuring correct system operation. Now, before we consider any actual steps or procedures for grounding a system, we'll review some of the simple terminology and an explanation for electrical grounding in accordance with the National Electrical Code, which again is the NEC. Now, the NEC is really the authority on electrical system installation here in the U.S., with a new version released every 3 years. The most recent version of the NEC was released in 2023, but you'll need to check which version is being enforced in your location or jurisdiction to ensure that your electrical system will be approved by your building inspector, as there could be significant variations from one version of the NEC to the next. And it's really important to adhere to local building requirements, as interpretations of the NEC could differ between jurisdictions or inspectors, with additional modifications outside of the NEC requirements potentially being enforced in your area. Bear these challenges in mind as we start to explore some of the essential terminology and requirements associated with solar photovoltaic grounding. Now, the terminology that's used to describe various components of a grounding system can be rather confusing, but must be understood in order to safely and effectively ground an electrical system. Article 100, Definitions, of the National Electrical Code, or the NEC, defines many of the terms that we'll use in today's video, all of which are relevant to solar photovoltaic systems. And so we'll start with the term ground, which is simply defined as the earth. And so anytime that we use the term ground or grounding, we're simply considering an intentional connection or a bond being made to the earth. So it follows that grounded is the condition of something that's connected to the earth, or connected to a conductive material that's in turn connected to the earth. So when we use the term grounded, we're connected to the earth or to some conductive body that extends to the earth connection. And this connection to the earth can be made with a grounding electrode, which is a conductive rod, plate, or wire that's buried in the ground, providing a low resistance electrical connection to the earth. In other words, it's a conducting object through which a direct connection to the earth is established. And Article 250, Part 3 of the NEC covers the material, shapes, sizes, and depths of grounding electrodes that will ensure adequate grounding for an electrical system. We'll explore the installation of grounding electrodes in another video, but here in this Article 250 Part 3, you'll see that the NEC allows for a number of different types of grounding electrodes to be used, including certain metal parts of an existing structure like buried water piping, UFR, structural steel, or concrete encased rebar. But the most common grounding electrode is a grounding rod, which is a long metal rod that's driven into the ground near the building. The type of grounding electrode used for any given application really just depends on the system specifications, the site characteristics, and the building codes being enforced in the area. You could also have multiple grounding electrodes for a single installation, with all grounding electrodes connected together to form a grounding electrode system in accordance with Section 250.50 and Section 690.47 of the NEC. In this case, all the grounding electrodes that are present are bonded together to form the grounding electrode system. A grounding electrode conductor, or GEC, then connects the grounding electrode to the rest of the electrical grounding system, and the GEC only carries electrical current during ground faults, so it should not be any longer than necessary. Grounding conductors can be bare or can have insulation that should either be solid green or green with yellow stripes. A grounded conductor then is a current-carrying conductor that is intentionally grounded to the earth. So this normally current-carrying conductor is bonded to ground. Grounded conductors should either be white or gray in color, with the negative or white wire within a grounded PV system typically serving as the grounded conductor, while the neutral white wire in a standard household alternating current or AC system generally being grounded or bonded to the grounding conductor at the main service panel. An ungrounded conductor, on the other hand, is a current-carrying conductor that has no connection to ground, or no connection to any conductive body that would extend to the ground connection. Ungrounded conductors can be of various colors, but must be distinguishable from the grounded or grounding conductors. So these ungrounded conductors cannot be white, gray, or green. The ungrounded conductor in a transformer isolated system would typically be the positive or red conductor, or usually a hot wire like the black, red, or blue wire within a standard household alternating current or AC system. Now, for safety purposes, an equipment grounding conductor, or EGC, connects any exposed metallic equipment that may inadvertently become energized to the grounding electrode system or to the grounding electrode conductor, which again is the GEC. In any sense, the equipment grounding conductor, or EGC, does not carry any electrical current under normal operation, but its low impedance enables it to carry a fault current should a ground fault occur within the circuit. Again, you may want to review our previous video on safe and effective grounding for more information on ground faults. But again, the equipment grounding conductor, or EGC, will typically be a green or a bare copper conductor that runs through the entire system, touching all the metal parts, including the aluminum rails, the edge of each PV module, any EMT conduit or metal raceway, as well as any electrical boxes, disconnects, and the inverter, among other system components. Now that we've reviewed some of the terminology, we'll look at some of the basic requirements for grounding an electrical system. While the NEC doesn't serve as a design manual for electrical systems, the various articles and codes encompassed within the NEC, as we'll see throughout this video, can be used to establish the minimum requirements for photovoltaic grounding. But again, since we can't address every code and every detail that's found within the NEC in today's video, it's always recommended that you consult with a licensed electrician, a solar professional, or your local authority having jurisdiction, AHJ, to ensure that all safety measures are practiced and all system requirements have been met. Article 250 of the NEC, Grounding and Bonding, provides the general requirements for grounding an electrical system, while Part 5 of Article 690, Grounding and Bonding, addresses some of the specific requirements for grounding a photovoltaic system. But as mentioned earlier, the NEC is revised every 3 years, so you'll need to check which version is being enforced in your area to ensure system compliance. The 2020 version of the NEC has, for example, been in effect in Maryland since May of 2023, although local jurisdictions within the state may adopt their own electrical codes, which could change periodically. So again, always check with your local inspector, the Department of Permitting Services, or your authority having jurisdiction, your AHJ, for specific information on what codes and what edition of the NEC is enforced in your area. These permitting guidelines for residential solar, for example, reference the 2014 version of the NEC, although this particular reference to section 690.41 actually comes from the 2011 NEC, requiring systems over 50 volts to have one current carrying conductor referenced or connected to earth ground, unless the system were to comply with section 690.35 for ungrounded arrays. Now, the grounded connection for most PV systems will be made within the inverter during the manufacturing process, not on site by the installer, so this particular decision on grounded and ungrounded arrays is often made by choosing either a grounded type inverter or an inverter for use in an ungrounded system. But it's also worth noting that the 50 volt requirement specified in this code is based on the temperature corrected maximum open circuit voltage of the system, not the system's nominal voltage. A nominal 12 volt standalone PV system, for example, would likely not require a ground conductor, while a nominal 24 volt system, on the other hand, could require a ground conductor, considering the actual open circuit voltage of the array could easily exceed 50 volts when operating under colder temperatures. You may want to review our previous videos on measuring open circuit voltage and or estimating system size for more information on voltage output and the effects of temperature on voltage output. But as ungrounded systems have become more common, section 690.41 was revised in the 2014 NEC, allowing PV systems of any voltage to operate as a grounded or ungrounded system. Additional revisions and subsequent editions of the NEC have likewise updated those requirements for grounded and ungrounded PV systems. Subsection 250.162a was, for instance, revised by increasing the lower voltage threshold for DC circuits and systems to be grounded from 50 volts to 60 volts to correlate with Chapter 9, Table 11b, and .110.26a1b. But once again, check which codes and which edition of the NEC is enforced in your area. Now, as we've seen in previous videos, any issues with this system grounding could pose a considerable risk of system damage or failure. Equipment grounding, on the other hand, can protect you from an electrical shock that might occur when contacting energized equipment, enclosures, or metal parts that may be under fault conditions. As such, equipment grounding bonds all exposed non-current carrying metal parts to ground, regardless of system voltage, to the PV system circuit equipment grounding conductor. This includes the exposed metal parts of the PV module frames, electrical equipment, and conductor enclosures in accordance with Section 690.43 of the NEC, which is a reiteration of the basic requirement for equipment grounding found in Article 250, Part 6, as for example Section 250.134 and Section 250.136. And this is important because improper equipment grounding could be dangerous and potentially fatal. Now, Section 690.47 addresses the grounding electrode requirements for photovoltaic systems. While there may be some level of uncertainty or ambiguity surrounding these codes, particularly in some of the earlier versions of the NEC, I'll provide my best interpretation and understanding of these grounding requirements, albeit briefly in today's video. But as always, it's advisable to consult with your local inspector, your permitting office, or your AHJ to ensure that your electrical system is to their satisfaction. We'll start with subsection A in the 2011 and 2014 version, which outlines the system grounding requirements for alternating current systems, which would apply to those PV systems having no field installed or accessible DC circuits, or to the AC side of a conventional PV system. The grounded connection in most residential systems, for example, is made by bonding the grounded or neutral conductor to the grounding electrode conductor in only one location, typically on a bus bar within the main electrical service panel. Subsection B in the 2011 and 2014 version of the NEC, on the other hand, applies to DC systems like the DC side of a photovoltaic system or a small standalone PV system supplying DC electrical loads. And in this case, the DC grounding connection would be made at a single point on the PV output circuit within the inverter for those systems having an inverter, or perhaps on either side of the DC disconnect or charge controller. But as we've discussed in previous videos, you want to avoid multiple DC grounding connections, as that could result in alternate current pathways and improper ground fault protection. Subsection C in the 2011 and 2014 version of the NEC then applies to the most common type of PV system having both alternating current and direct current grounding requirements. And in this context, the DC and AC circuits are considered to be separate systems without a direct connection between the DC grounded conductor and the AC grounded conductor. And so these two grounding systems must be bonded together by connecting separate AC and DC grounding electrodes with a bonding conductor, or by connecting the bonded DC and AC grounding systems to a common grounding electrode using an AC grounding electrode conductor, or even by combining the DC grounding electrode conductor and AC equipment grounding conductor with a continual run. Now, with that said, there's still some uncertainty in these earlier versions of the NEC, particularly if subsection B applies at all to a PV system with DC source circuits running to an inverter with an AC output, as well as if subsection C applies at all to ungrounded PV system inverters, which have been known to have no common grounding electrode connection terminal to connect a grounding electrode conductor. But along with the growing prevalence of ungrounded PV arrays with their non-isolated or transformerless inverters having no DC circuit conductors connected to the ground, the 2017 NEC and subsequent versions has simplified a lot of this terminology that's found in Section 690.47. For starters, subsection 690.47a requires those buildings or structures supporting a photovoltaic system to have a grounding electrode system installed in accordance with Part 3 of Article 250, which specifically addresses the grounding electrode system, types of grounding electrodes, and electrode installation requirements. And we'll talk about some of these factors in a moment. But in any sense, this cross-reference was updated to subsection 690.47b in the 2023 version. The equipment grounding conductors of the PV array are also to be connected to a grounding electrode system in accordance with Part 7 of Article 250, Methods of Equipment Grounding Conductor Connections. And starting with the 2017 edition of the NEC, a distinction has been made between the grounding requirements for functional grounded PV systems in subsection 690.47a1 and solidly grounded PV systems in subsection a2. A functional grounded PV system has an electrical reference to ground that is not solidly grounded in accordance with the definition that's given in section 690.2. That's why we often refer to functional grounded systems as not solidly grounded. And with that said, most PV systems in existence today, for general use at least, except for very large power plants, are functional grounded, as defined in this code, with the ground reference for most systems typically established through a resistor or a fuse that's part of the ground fault protection system that's required through subsection 690.41b. See the new informational note after subsection 690.47a for additional details. In any sense, a functional grounded system with an interactive inverter output is grounded to the building grounding electrode system when the equipment grounding conductor for the AC output of the solar array terminates or is connected to the grounded AC distribution equipment. In this case, all the metal parts are bonded together, with everything being grounded by connecting the equipment grounding conductor to the earth, and this can be the only ground connection with any functional grounded system. The additional auxiliary grounding electrode for array grounding that was required in subsection 690.47d in the 2014 edition of the NEC was relocated to subsection B starting in 2017 and is now permitted rather than required in accordance with section 250.52 and 250.54. This auxiliary grounding could include the support structure for a ground-mounted array per section 250.52 and or the metal frame of a roof-mounted array per subsection 250.52a2 according to the 2017 version of the NEC, or 250.68c2 according to the 2020 and 2023 versions of the NEC. And while the inclusion of an auxiliary ground rod at the array is not in violation of the 2017 NEC or subsequent versions of the NEC, an auxiliary ground rod could give rise to a dangerous earth-ground potential between the separate earth connections, as we discussed in a previous video. Now, we'll briefly cover some of the basic sizing requirements for photovoltaic grounding. In previous videos, we considered grounded and ungrounded conductor sizes, but in today's video, we'll consider the size of the equipment grounding and the grounding electrode system. Just note that many of the codes that we'll discuss in today's video represent the minimum requirements that may or may not be adequate for all project designs, scopes, and sizes. Looking at section 690.45 of the NEC, for instance, we'll see that when ground fault protection is used, as detailed in section 690.5, the equipment grounding conductor will be sized in accordance with section 250.122 based on the rating of the overcurrent protection device that's protecting the circuit's AC or DC conductors. If the overcurrent protection for a PV output circuit was 30 amps, for example, then a 10-ohm copper conductor would be required. A 400 amp fuse or circuit breaker protecting inverter to battery conductors, on the other hand, would require a 3-ohm conductor. And as we've seen in previous videos, a low resistance or an impedance will trip the overcurrent protection device, effectively preventing the conductor from overloading or burning out whenever a ground fault occurs from any backfed current coming from, for instance, a battery, a line tie inverter, or parallel strings. It should be noted, however, that the equipment grounding conductor sizes given in table 250.122 do not account for voltage drop. With that said, if the ungrounded conductors have been oversized to reduce the voltage drop within a system, then the equipment grounding conductor should be proportionally increased in size in accordance with 250.122b, except when required by 310.15b for temperature correction or 310.15c for conductors in a raceway or cable. Again, these factors have been discussed in some of our previous videos on wire sizing. Now, when ground fault protection is not used, an assumed overcurrent device rated in accordance with 690.9b is used when referencing table 250.122. In that case, the equipment grounding conductors for the PV source and output circuit should generally be sized to carry at least 125% of the short circuit current from the PV circuits, not including backfeed currents from other sources. With these factors in mind, the equipment grounding conductor in a PV source and output circuit should generally be at least 14 Og, or commonly 10 Og, in order to provide some degree of mechanical strength. The conductor could be increased to 6 Og, however, if there were any possibility of physical damage. A conductor smaller than 6 Og, on the other hand, would generally be protected with a raceway or cable armor in accordance with 250.120c. Now, per subsection 690.47b, grounding electrodes and grounding electrode conductors, a grounding electrode conductor, which physically runs from the ground rod to the service panel or wherever it's being terminated, shall be sized according to section 250.66. Here, the size of an AC grounding electrode conductor will generally depend on the size of the conductor that's feeding the AC load center. Based on table 250.66, for example, a 6 Og grounding electrode conductor will suffice for main AC power conductors up to 1 aught Og copper, while a 4 Og grounding electrode conductor will suffice for AC power conductors up to 3 aught Og. And just like we noted previously, no metal covering or protection is required with 6 Og or larger conductors that are not exposed to physical damage as specified in subsection 250.64b. Section 250.166, on the other hand, establishes the size of the DC part of the system, primarily based on the grounding electrode that's being used. Small residential and commercial PV systems, for example, may only require a 6-AUG grounding electrode conductor with a typical grounding rod, or a 4-AUG grounding electrode conductor when using an existing concrete encased electrode. So for many PV systems, a small 6-AUG grounding electrode conductor will be allowed if it's the only connection to a rod, pipe, or plate electrode, in accordance with 250.166C. But in some cases, the DC system grounding electrode conductor cannot be smaller than 8-AUG, or the largest conductor supplied by the system, in accordance with 250.166B. With that said, most PV systems will require a careful assessment of DC, AC, inverter, and utility grounding requirements. With that said, I hope this video has provided a basic understanding of what's involved in grounding a code-compliant photovoltaic system, not only to meet system requirements for inspection purposes, but also to ensure a safe installation. While we've only scratched the surface on this topic, in upcoming videos we'll consider additional aspects of photovoltaic grounding, including grounding electrode requirements as well as some practical installation guidelines. But as always, it's recommended that you consult with a licensed electrician, solar professional, or your local authority having jurisdiction, AHJ, to ensure all safety measures are practiced and system requirements are met. You can subscribe to this channel to stay connected on upcoming episodes of the Solar Clips video series, but in the meantime, please visit our website for more information on solar photovoltaics and other energy-related topics.